Okay, this experiment is about internal energy, but also in terms of heat loss, energy stored, and energy transfer. And what we're going to do is basically the experiment that you did at GCSE, but start thinking a lot much more deeper about it. So we're going to take some blocks. We have some specific heat capacity blocks. They are two completely different materials. We've got aluminium, we've got copper. They're both very good conductors, very similar in their conductors, their ability to conduct. And normally they are the same mass, so they're a kilogram each. That's 1,001 grams. That's 999. So there's 2 grams in it. This has 2 more grams of matter to warm up, a lot more molecules inside to warm up. And what we're going to do is look at how much energy is needed by each of those molecules inside. We can actually work it back to the molecule level, but how much energy is needed to heat up the material itself, how much energy can be stored internally in these substances. Now we are going to record it, so rather than using thermometers, even the more sensitive one with the bigger intervals between the readings isn't sensitive enough. So we're going to take it off a data logger and we're going to run it over real time. So I'm going to get you to take the readings, record them, and think about how that works. Now, we're going to do this at room temperature. We are going to obviously have heat loss. If you go back to, again, probably the first experiment you ever did in science, cooling curves. If you have something that is hot, then if it's hotter than the surroundings, if it's at a higher temperature than the surroundings, then it has more average heat energy. That energy will dissipate, it will come outwards. Okay, and the cooling curve, which is actually something called Stefan's fourth law, means that the bigger the temperature difference above the surroundings, the faster it's going to cool. So in the same time, the rate of cooling is bigger at the beginning, gets smaller, gets smaller. So the rate of change of temperature is much bigger if you've got a bigger temperature difference. Now obviously, when we heat these, we're going to have that temperature difference. So there is some tricks we can do to think about it, but we can of course put insulation around it, so we've got a good insulator. We also have a silver surface to reduce the radiation, because radiation is the main way in which the heat escapes. But we also have conduction and convection. That's not going to stop it, that's just going to slow the process down. So even though we both have the same put around and we're not going to bother covering the tops, we're just going to actually work around the basis that temperature loss is happening all the time, but the higher the temperature above the surroundings, the more you're going to lose each second. So there are tricks. If we could, we don't have the facilities here because everything's been shut for a while, but if we could, what I would do is reverse this. If I take this so that temperature 1 is below temperature 2, below the surroundings, so if I was down, then these arrows would be reversed. You'll be absorbing the heat and you get exactly the same curve flipped round. So if we had a temperature much lower than the surroundings, let's say 10 degrees lower, then it's going to gain a certain amount of heat to warm it up from the air. If we take it to then 10 degrees higher, it's going to lose that same amount of heat back into the air. So even though we are not actually preventing heat loss, if we make the heat loss and heat gain from the surroundings the same, then what we can do is make sure that they actually produce the same amount of heating. Okay, so we should get a much more accurate value of actual readings. Okay, we're all set up and ready to go. Both power packs are set to the same voltage, so they're giving the same current. And what we're going to do is just going to turn them on and I'll read out the readings. So I'll get it all up and running first. I want you to plot the values for the 2 thermometers from here, and you're going to need to plot them against time. So you'll need all 3 readings and we'll let it run in real time. The red reading is for the aluminium block and the blue reading is for the copper block. Okay, so again, just remind you, 2 more grams to heat up there, so let's see if that makes a difference. Out of 1,000, that's going to be 2 out of 1,000, that's going to be 0.2% error on the mass. So if we turn them on and we'll start plotting, and we'll start the time. Okay, so they're both about the same temperature, not quite the same. Aluminium's slightly warmer at the moment. As these plot over time, we'll have a graph here, but it's too small a scale, so you're going to need to plot one, and it's all about how you put your line of best fit. It will have bits that are curves, definitely, and bits that are straight. Okay, so we'll have a look at those, but I'll let you run in real time. The current is running at 3.75 amps. So 3.75 amps of current. And the voltage is 12.5. I'll give those data on a whiteboard in a second. Okay. Popping at the bottom of the screen there the two readings that you'll need. So those are your two numbers, those in amps and volts, and those you'll need to get your power going in, so the rate of energy supply to the two blocks. Right, leave you to watch and take your readings. Okay, that's been running for over 10 minutes now, and if we can look at the graph appearing, when you plot this, you should be able to see, hopefully, a lovely graph like this. Same power input. Obviously, the two metals are behaving differently in terms of how their energy starts. So, what we'll do, just turn those off and stop running. You've got all your data there for the first 10 minutes, so let's just take those readings. You'll see that you've got a definite curve at the beginning. Is it linear from there? Get a big scale graph and you can see more precisely. My suspicion is that there will be heat loss increasing as you go higher up, so it will curve ever so slightly. So think about how that you represent that in your graphs. Are you going to curve it? Are you going to do a straight line of best fit? And also have an adaptation about your thinking as well. So same energy in each second, but one's rising greater rate. So how does that tell you about the specific heat capacity of the material, and perhaps the heat loss from it? After all, one of these materials is a bigger volume than the other because it's less dense. Does that make a difference? So you can have a consider there. So with your results, you'll be able to get a value for specific heat capacity. As I say, the voltage and current, just a quick reminder, are those into both meters. Into both heaters. And as I say, we've maximised things without cooling these down at the beginning. We've managed to try to maximise the efficiency of it, so we get more accurate results. Okay, so plot those and see how it goes. Thank you.